Hey, welcome back. Today let's talk about what we're going to learn. You're going to learn how to predict the landing spot or speed of an object in projectile motion. We're also going to talk about what projectile motion is, I guess. Our standard is constant acceleration. The equations of motion are, we've had these, but now we're going to use them in the terms of y's and x's specifically, and their acceleration. When solving two-dimensional kinematic problems, each component is treated separately. The time is common to both. And what we mean by that is, in this object, the time it takes to go forward is also the same time it takes to fall. So when something's in projectile motion, all right, an object projected horizontally has initial velocity in the horizontal direction and acceleration due to gravity in the vertical direction. The time it takes to reach the ground is the same as if it were simply dropped. So what we're saying here then is, what we want you to know is, initially this object has only x velocity. There's no acceleration on it initially in the x direction. It has only an initial x velocity, so it takes off going straight forward to start off with. After a certain amount of time, obviously gravity has an effect on it, and it's also starting to fall. So now the vector is going, this is the velocity it's going, in the speed in the direction. It still has that same x component. Notice that we've made these be the same length, but now it's gaining a y velocity. It's gaining, and that's in the negative direction, so we have this small y vector. A moment later, some moment in time, it still has the same x vector velocity, but now because gravity's been pulling on it longer, the y vector has increased, so it's now going faster in the y direction. And then as time goes on, the x velocity is not going to change. That x velocity stays the same, but the y velocity is going to keep increasing. So that's why our y vector, no y vector, small y vector, bigger y vector, very large y vector. Notice the x vector stays the same in each one of these cases because it's not going to change. There's nothing in the x direction that's accelerating it. So as soon as we let go of it, students always say, well, what about air resistance? Well, air resistance on most things that we're going to shoot out or throw is going to have minimal effect on it. Projectile launched in an arbitrary direction may have initial velocity components in both the horizontal and vertical directions, but its acceleration is still downwards. So let's look here. We've got a golfer hits a ball, all right? And initially it has an x velocity and a y velocity. That's why it goes up and forward. But what happens as time goes by? Well, the y velocity, because gravity is pulling on it, starts to slow down. The x velocity is not going to change, again, because there's nothing accelerating or slowing it down in the x direction. It's going to keep going forward. At some point, once it gets to the top, it stops going up anymore. It loses all of its y velocity. Gravity has canceled all of that out. And the reason it starts coming down now is that it starts to gain velocity in the y direction, but it's now downwards. The x vector, again, stays the same length the entire time. Here what we see is whether we throw it up at a 45-degree angle or throw it down at a 45-degree angle, and they're just choosing these two angles arbitrary. They could have just simply put a theta in there to let you know any angle. What they want you to see is that the motion, once it's let go, is going to be the same. We have these two, and they're the same distance. This right here, they have the same distance between these two all the way through. Alright, so if we were out in outer space, and the reason I say that, because in this case we want to have no air resistance, so we obviously can't achieve that in very large areas at all here on Earth. But let's just say we could. Maybe we're hitting a golf ball up on the moon. Alright, so if we were hitting a golf ball on the moon, the optimal angle or launch angle to get the maximum distance would be a 45-degree angle. All right, notice here's our 45-degree angle, and it ends up going farther than anything else. That's true, though, again, for no air resistance. When we do have air resistance, so here's a drawing of when we do have air resistance at 45 degrees. Here's with no air resistance. So when we do have air resistance, we want to shoot at an angle that's slightly less than 45 degrees to get the maximum distance. So you can see there's a big difference between air resistance and no air resistance with the 45 degree angle and shooting slightly less than 45 degrees. Alright, projectile motion. We're going to basically use these two equations. YF equals YI plus VIT plus 1/2 GT squared, and XF equals XI plus VIT plus 1/2 AT squared. 90% of the time, and maybe not quite 90, maybe it's 85, 80% of the time, but I think you get the idea that it's going to be simplified down into these two equations. And let's talk about why. Well, a lot of the time we're going to simply say YF is when it lands. All right, YF is it lands. So YF is going to be 0. All right, YI is just the height. So a lot of times we'll replace YI with an H. And you see that a lot in your algebra classes. They use H. In true projectile motion, usually there is no Y velocity, so the Y velocity in this case goes to 0 as well. So that part goes away. And all we're left with then is 1/2 GT squared. Well, as you can see, we get 0 equals H. This part goes away, 1/2 GT squared. In the X direction, all right, for projectile motion, usually we set up our thing. If we have this thing that's shot off like this, usually we'll use this as our coordinate plane, and xi becomes 0. The initial velocity is what we have to start off with, and we say that there's nothing accelerating in the x direction, so we typically get rid of this as well. So that leaves us with just xf equals VIT. Now, we can't always use these equations. A lot of times it's going to be simplified down this, but I want to make sure we point out that we simplify it down into these equations instead of just starting with these equations. So here's our first example. A motorcycle is traveling 20 meters per second. So a motorcycle would be going in the x direction. So this is my initial velocity in the x direction is 20 meters per second. It runs off a cliff. It lands 140 meters away from the bottom of the cliff. So XF equals 140 meters. Find the height of the cliff. So we want to find, that's YI. If it lands on the ground, we can assume YF to be 0. VIY, because it came off the cliff. So here's our cliff. I'll put an example here. Here's our cliff. The motorcycle, whatever, goes off the cliff. So that has no Y velocity. It also has no acceleration in the x direction. But what is going to accelerate it? Gravity is going to make it come down. So gravity is negative 9.8 meters per second squared. So I'm going to write my two equations here. Now from here then I'm going to plug in what I know. XF is 140. XI we said is 0. Alright, that's where we're going to start. I didn't write it up here, but I should have. XI is 0. We can say our cliff's right there. XI is 0. The initial velocity in the x direction was 20 meters per second times t, and there was no acceleration in the x direction. So there's my one equation. Then I go to my other equation, YF. Well, that's 0 because it landed on the ground. YI is what we want to find. A lot of times we'll replace that with an H. I'm going to leave it YI right now. I don't know. I probably could put it as an H. VIT plus, there is no velocity in the y direction. And we're left then with 1/2 g, or half of negative 9.8, or negative 4.9 t squared. So here's our two equations. What I want to point out to you here then is that my y equation has two variables. I can't solve for two variables at the same time. So I'm going to go back to my x equation, all right, and I have one variable, just time. So if I divide both sides by 20, we get t equals 7 seconds. Now, because the time that it took to go forward, or the time it took to go that 140 meters, is also the same time it took to hit the ground and land at the ground, or 0, that's the same time. I can come over here and say 0 equals yi plus negative 4.97 squared. From this we get yi equals 240.1 meters. So yi, or the height, turns out to be 240.1 meters. So what did you learn today? All right, we learned how to predict the landing spot or speed of an object in projectile motion. One of the things I hope that you walk away from here is that maybe you've realized in these types of equations, when it asks me to find the height, that's a y component, height is y, you're going to end up using the x equation to solve for t. If it asked me to find the distance the motorcycle went, then I would end up using the y equation to solve for t. And we can talk more about that tomorrow, but basically it comes down to the number of variables. If it's asking me to find the height, that means there's going to be the height variable, which means there's going to be time and height. If it asked me to find the distance the motorcycle went, that means there'd be distance and time. So there'd be two variables there, so I couldn't use the x equation in that case. Hopefully this was beneficial. I'll catch you guys on the flip side.